these are the mechanisms, and the mechanisms are quite well defined. Then, of course, next to just having mechanisms, it's also very important that we have interventions. And that's also where we are working on at the National University in Singapore. And interventions can be, for example, medications we are given, which are already there, or small molecules, or dietary interventions. And one of the dietary intervention I will come back to is alpha-ketoglutarate, and that has been shown if you feed alpha-ketoglutarate to mice, that these mice live longer, which means that we can identify individuals, how they are aging, and we can intervene. And that has led to ICD-11 codes, which means that aging and age-related consequences are now a disease. So we can actually, in clinical practice, use this international classification of disease codes. And since a couple of years, in 2018, it was introduced. It was a long way to have an ICD-11 code for aging, but we got it, which is quite nice. So here's the summary. So we are aging during the life trajectory, and it starts very early. Then normal care would have specific disease prevention and specific disease treatment. However, we would really like to slow down the aging process by all the mechanisms in the bottom part of this slide, and therewith prevent the onset of age-related diseases. And I think you will agree that this is quite attractive, because nobody wants to be sick. And that's also the reason why there's lots of investment at the moment in the field in healthy longevity, or in geroscience, or in the field of health span. And here you just see how many business partners we have worldwide, and how academia is really working together with small SMEs, so small businesses, or larger businesses, and of course also regulatory actions. But it's I would say a booming business in the interference of science hubs like NUS, like investors and other companies to make business, because everybody here in the room and everybody worldwide is aging at this moment in time. We also make great efforts to really stimulate academic research, and we are doing that, for example, by the Longevity Science Foundation, which we just founded. And I'm in the visionary board of this Longevity Science Foundation. I think it's a great initiative to really give funds to real good academic science to bring the longevity medicine field further. And the aim is of the Longevity Science Foundation to get around about 1 billion in 10 years. Please look at the website for further information. So first, I would like to dive a little bit deeper in the identification and then in therapy, what we have in hands at the moment. So how can we identify individuals who are aging gracefully and maybe who have some problems with the aging process? And there I have to give you another keyword next to health span, very important to mention, is biological age. Biological age is different from chronological age. So biological age is reflective of the pace of aging of a human body. So you see two examples here, two ladies at the age of 80, and you see that the one is very physically active and has a different shape, different activities compared to the lady on the right-hand side, which means that it's very likely not only that the right lady has more chronic diseases, but also that the aging process is much faster compared to the lady on the left-hand side. So the chronological age is quite different from the biological age. So, and then we have to quantify that already. But we are quantifying, I would say, biological age already in clinical practice. And I would like to show you these photos of individuals. And what you can see on the upper panel are, of course, female, on the lower panel are the males. And I would like to give you 2 seconds in silence to actually see what you see, or formulate what you see. And I think while looking at these persons, you will recognize that the ones on the left-hand side, they are much younger compared to the ones on the right-hand side. And what do we do in normal life, but also in clinical practice? When we look at people, we look how they look like. And we do that while really looking at, for example, the skin color, we're looking at wrinkles, we are looking at the hair color, we are looking at the hair shape, we are looking at the expression, if somebody is smiling or not, and what kind of eye contact, for example, somebody has. And then we are using all this information to judge people on their facial age. And that was done also with other individuals. They got a couple of thousands of photographs of individuals, and they had to judge what their chronological age is. And in the end, they judged, of course, the ones on the left-hand side much, much younger compared to the ones on the right-hand side. However, these are all individuals at the age of 45. And so the outer side of the human body, the facial age, can be quite different compared to the chronological age. And these are individuals of a cohort study, of the Dunedin study in New Zealand, where they photographed all individuals at the age of 45 being part of the study. And the study is a very nice one because already at the age of 26, they included individuals of Dunedin, of that little city in New Zealand, and they asked them, do you want to participate in this longitudinal studies? And lots of participants at the age of 26 living in Dunedin actually agreed on it. And at the age of 45, this was the result, how they look like. So the facial age is quite nicely already associated with other parameters. And I will show you the other parameters. So here, again, the same study, the Dunedin study. And what they did, they followed the participants from the age of 26 to the age of 45. And then they measured all the things at the right-hand side, so BMI, waist-hip ratio, leptin, lots of blood markers, but all markers which could be done in clinical practice already. For example, by every GP, I could do it as internal medicine specialist tomorrow with my patients. And what they did, they plotted the outcomes of these measurements over the time. And what you see in the graph is lots of lines going up, and that means that the bodily function is going down, so it's getting worse. And what you see that all the parameters, if you look at, for example, blood pressure, or you're looking at BMI, everything is trending to the worst side of life. So to a negative side, which means that already at the age of 20 to 30, something is happening in our body, which is called aging and can be measured already in clinical practice. And you see that there's a huge change until the age of 45, which means that most of us here in the room are aging at this moment in time. And these parameters, of course, are biomarkers, or very nice biomarkers for diseases. For example, cardiovascular disease or diabetes or dementia, etc., which means that aging is starting very, very early in life. They used all these data to also to calculate a biological age score, which is given here. And that's what they did at the age of 38. So all the parameters, everybody is chronologically 38, but biologically, somebody at the age of 38 can be 28 or can be nearly 60. So already at early age, we are able in clinical practice to calculate a biological age and maybe also to interfere. And then, of course, it's the question, what kind of underlying mechanisms is behind of it? And my group was especially interested in cellular senescence, which is, once again, if a cell is not replicating anymore, but stays in the body and negatively influences the body. And we asked the question, is cellular senescence associated with chronological age? And in which organ system within individuals? Might it be that the heart is more attacked by senescent cells, or the brain, or the pancreas, etc.? So we looked at all information worldwide, and what we found is, you can see that in this figure on the horizontal axis, all the organs, and then on the vertical one, the magnitude of the association. And what you can see, nearly every organ, there is an association of cellular senescence and chronological age, which means that you accumulate in organ systems with chronological age senescent cells. But the association is the highest in the pancreas and the brain, which means that these organ systems might be attacked much more compared to others with cellular senescence. And if we are looking at these organs, what are these organs doing if they are failing? There will be diabetes and there will be dementia. And these are also the diseases who are very associated with cellular senescence. And that might be then, of course, a target also for interventions. We also looked if, for example, cellular senescence is associated with facial age. And yes, we were able to find it. We looked, for example, at Rimple scores. It's the same as they did in the Dunedin study, but we did it already 15 years ago, where we made photographs of individuals, participants, and we also took skin biopsies of them and looked at senescent cells. And what we found is if somebody is looking older, judged by a panel, then they are more likely to also have senescent cells, much more in the inner upper arm of their body. And if somebody has, for example, more wrinkles, as one of the examples, more wrinkles also associate with more senescent cells in the inner upper arm, which means that the outer side of a human body also reflects the inner side, how the aging process is occurring. And senescence, cellular senescence, is also associated with age-related diseases. This is another piece just recently published, where we looked at brain disease, eye disease, endocrine diseases, heart diseases, etc., all the age-related diseases frequently present. And we looked at, is there more expression of markers of cellular senescence in individuals who are suffering from these age-related diseases compared to controls. All the blue dots are significant associations. Everything is red is not significant. And what you can see, there's an overwhelming evidence that age-related diseases are associated with cellular senescence in humans, which is quite nice. So it's associated with chronological age and with diseases, and also how you look like. Cellular senescence is quite challenging to measure in clinical practice because you have to take biopsies, etc. So there's lots of investigations also at other measures of biological age. For example, looking at transcriptomics or blood chemistry clocks, etc., but also as methylation. So the question is, out of a blood sample, can we actually measure how somebody is aging, and can we develop clocks? So can we really determine how old somebody is? And I would like to show you a couple of studies about the methylation clocks, because that's easy to measure. What is methylation? Methylation is very important in the genetic field. So you have methylated DNA, our genes, and methylation can occur at GPC sites. And if these are methylated, then this methylation can actually regulate if a gene is going to be active or not active, which means that such a methylation can switch a gene off or on. And that's very important, because if we could regulate methylation, that means that we can also then regulate what we want to express in terms of our genetic makeup and what not. And that has led to lots of studies looking at epigenetic clocks, which means the methylation site on our DNA in different manners. And since round about nearly 8 years, we have lots of these measurements in different cohort studies and different clocks being evaluated in human beings. And you see there were already clocks where they looked at methylation sites in humans in 2013, 18, 19, and there are lots out there at the moment. And recently, a very nice review summarized all the results of epigenetic clocks. So is methylation associated with outcomes in humans? Yes, it is, and independent of what kind of clocks you are looking at. So you see different clocks here, and in the circles you see different outcome parameters. So it's associated with smoking, with depression, poor lung function, lots of age-related diseases like cancer and cardiovascular disease, but also mortality. So how our genes are methylated is very predictive of how an outcome is in human cohort studies. Very importantly, it's very important that methylation is very different in different organ systems. There's lots of overlap if we are looking at lung, brain, liver, muscle, and colon, which is depicted at the yellow and the blue part. Blue means low DNA methylation, so the number of methylation sites on the gene are quite low, whereas yellow means lots of methylations, and they are quite similar in parts of the organs. However, there's also a huge chunk of data where we see that different organ systems are differently methylated, which also makes sense, because if you're looking in the colon, a colon might need other expression of genes compared to a lung, which will all make sense that it's not the same in our entire body. Because of the predictive power of these kind of methylation clocks or epigenetic clocks, there are lots of companies also now investing and already advertising that you could measure your biological age based on the epigenetic clock and based on your methylation data. And I have absolutely no relation with Mudo, but Mudo is in UK. and really advertises to measure the biological age based on methylation clocks, based on salvia biosampling. So there is a huge action out there, and people already measuring their methylation age. A very nice initiative is also that all the clocks are now coming together in the Clock Foundation. So have a look at the website if you're interested in clocks, to bring the evidence together to make the one better clock out of all the data we have. So this is a very nice academic exercise and initiative. So if you have all the clocks, then also you would like to do something and going to the interventions, and lots of small medium enterprises already doing that. For example, Molecular U, they are basing it, they're phenotyping individuals based on their transcriptomics and on their blood results, and then already giving advice how you can change the clock and how you can make you younger. And in the end, the entire concept before really going to the interventions is summarized here. So you have a sort of a good phenotypic characterization in terms of genomics, epigenomics, transcriptomics, so everything you can measure of the human body. And then you are merging that together with already the phenotype, the disease phenotype, for example, and then you are building the interventions on that. And the interventions can either be lifestyle or can be medication of small molecules with new drug interventions. So that brings me to the next step. What kind of interventions can we do already? And one of the very important interventions is lifestyle. And of course, we already know that. So we don't have to wait until we implement, for example, longevity medicine interventions into clinical practice, because we have them on hand. This is, for example, reducing sedentariness, to reduce hypercaloric diet, fat excess, etc. So lifestyle is the most potent drug already we have, or if you would call it drug or intervention, to reduce the biological age. We know that there's a huge amount of evidence that bad lifestyle is interfering with the hallmarks of aging. So all the influences you see, again, telomere attrition, you see proteostasis, all the mechanisms I have told you. We also know that from epidemiological studies that a healthy lifestyle is really associated with a longer life, and not only a longer life, but also a healthier life. And I just show you here results of the Rotterdam study that you will add 6 years of a longer life, but also very nicely a healthier life if people have a healthier lifestyle. So that's very important. Is there enough evidence that we can say, yes, lifestyle, for example, more physical activity, less sedentary behavior helps to remove negative effects of the aging process from our cellular system? I show you here one of the results. It's not my study, but I really like the study because it's so simple. What they did is 50-year-olds, sedentary individuals, quite healthy but sedentary. They were asked to do a treadmill training, which means running for a couple of months, 6 months, and not 6 months running, but a couple of times a week. And what they looked at, if the telomere length and the telomerase activity and P16 is a marker for senescence, if that's changing over the course of that physical activity and exercise training regime. And what you can see in the panel A is that the telomere length is not really changing over 0 to 3 months, but it's much higher at 6 months, and longer telomeres is a good sign. The telomerase activity is going up, which is also good. All has been measured in blood samples, and P16 is going down. So this is also good. So P16 is a senescence marker. So that was much lower in blood samples when taken after 6 months of training on a treadmill, which is, I think, quite nice. We also know that physical activity is really associated with bad outcomes in human populations. This is a very complicated meta analysis, a little bit an umbrella analysis. What we did in the past 2 to 3 years, we really wanted to see what is the effect size of, for example, 1 step more somebody takes on certain life events somebody has. So the determinant were steps, our physical activity, or activity counts, or total physical activity, or a low physical activity or sedentary behavior, all measured objectively with either smartwatches or accelerometers or pedometers, so really objectively being measured. On the other hand side, we have outcome parameters, and the outcome parameters are mortality, activities of daily living. Jana, could you mute yourself, please? And frailty, falls and fear of falling, muscle strength, muscle power, and global cognition. So these are very important outcome parameters in human beings. And then we looked at the associations and published them independently. You see that on the left-hand side, what the association is of steps, for example, with frailty. And what you can see in the slide, in the figure, are circles. And the circles, if they are darker, if the color is darker, means that they have a higher effect size. And if the circle is bigger, that also means that the effect size is higher. So a darker circle with a larger circle means that there is a most strong association of, for example, steps with the outcome parameters. And what you can clearly see is that there's a huge, most strong association of the number of steps we take with frailty, with the chair stand test, with lower body muscle strength, and also a little bit with global cognition. And these associations are much stronger compared to sedentary behavior. So, which also means that public health interventions should really focus on increasing the number of steps, then rather reducing the number of sitting time, which is sedentary behavior. And of course, we should reduce the number of sedentary behavior and how many hours we sit. But most important, in terms of the effect size of the evidence, we have to increase our number of steps we are taking every day. And that's a linear relationship. This is also what we did in a couple of studies in Europe. For example, here where we asked individuals to increase their physical activity and muscle strength interventions in their daily life. So this was a pan-European study, EU study, Prevented, it was called, where we asked individuals at the age of around about 60 to increase their physical activity in their daily life, to improve muscle strength and balance, but also in total their physical activity. And what we asked them, do a couple of silly walks per day on the street, outside, and enrich your physical activity with everything you're doing during lifetime. For example, if you're brushing teeth, do that on one leg, because you will exercise your balance and you will have an improved balance, and therewith reduce your number of falls and fractures later in life. So there are lots of Europeans now who are brushing their teeth on one leg, because what you're doing while brushing your teeth, you're just looking at the mirror, you're looking at yourself, how old you are, and you can do that together with exercises. If you are waiting, you can do lunges, you can do squats, etc. So we don't have to per se go to a gym, but we can introduce everything into daily life. This is also what we are doing at the moment in Singapore in the SINGAR study, where we really try to adapt intake. We really try to have a more balanced dietary intake, a little bit dependent, of course, of the individual less, but especially lots of proteins and good food. We try to increase physical activity, and therewith we try to reduce risk factors for cardiovascular disease and also for dementia, and the primary outcome is dementia. So that's the SINGAR study. You might already know that lifestyle is really the key. So really now for the next coming 5 to 10 years is how to implement it. Most importantly is that we also have other interventions, and that, for example, repurposed drugs. Why are repurposed drugs so important at the moment in the geroscience field? Because they're already available. We have, for example, metformin, we have lithium, we have other medications who might interfere with the aging process. We know how they work. We know that what the safety profile is, which is very important, and they are quite cheap, which is important because we think that everybody, 100% of the population is aging at the moment, so we need cheap medication for it. And one of the really prototype studies within the aging field is being done by Professor Nir Barzilai in New York, in US, where he is giving metformin to relatively healthy individuals with no diabetes. So you know that metformin is an anti-diabetic medication. So he is giving metformin because of his action in the glucose regulation system and proteostasis and mitochondrial function on the aging process. He is giving this drug to 70-year-olds for 6 years in a randomized controlled trial to hopefully see that the incidence of comorbidities is going down, which means a lower incidence of cancer, cardiovascular disease, dementia, and mortality. He is targeting the age of 70 roundabout. We at the NUS, at the Center for Healthy Longevity, we are targeting individuals much earlier at the age of 40, because we think that we would like to prevent the occurrence of the first age-related disease already. And how are we doing that? Where do we get our evidence from? From lots of systematic reviews. We also wrote in the past. Here is one example where we looked at medication, which are already there, influencing proteostasis, and there with who might have a good influence, for example, of one of the outcomes of aging, and that's cognition, to improve cognition. And on the left-hand side, you see all the drugs we found, which are already tested, animal models, for example, lithium, of rapamycin, of rifampicin, or GM-CSF, doxycycline, etc. And what you can see on the left-hand side are animal studies, and the green dots represent positive studies with a positive result, which means improved cognition, and the black dots are negative results. And the X's are studies which are ongoing in humans. And what you can see that there's a vast amount of evidence already that medication modifying proteostasis might work to improve cognition in animals and in humans. We then look at other kind of drugs, for example, nutrient-sensing drugs, which includes, for example, metformin. It's a little bit different. We also looked at the improvement of cognition. Everything is red is negative, everything is green is positive. So what you can see, and I would like to focus your eyes on really the studies being done in humans, because the animal studies seem to be quite positive, but there are already a couple of human studies which are a little bit more negative than positive. But there are a huge amount of drugs already with lots of potential, for example, growth hormone, and in other things which have some positive results in humans already. So we are digging a little bit further what kind of drugs to use in the next trials. There was a study which was not done in my lab, but I would like to show to you that we are also now working on cocktails of medication. So combining them to really see if we can alter the biological processes. This study included 60-year-old men, 10 of them healthy, where the primary outcome was the epigenetic clock, so the methylation data, and they gave these individuals growth hormone, a little bit of testosterone, metformin, vitamin D3, and zinc for 1 year. And after 1.5 years, they looked at the epigenetic alterations, so the epigenetic clock. And what they found is, as the primary outcome, that these individuals were 2.5 years younger epigenetically with that epigenetic clock after having that cocktail of medication. So these are all repurposed drugs. Then we, of course, there are also lots of works internationally with new drugs, for example, senolytics. So you know that the senescent cells are associated with chronological age and with disease and how you look like. So the question is, can these cells be removed? Yes, they can be removed by using senolytics. So senos is old and analytics is removing of cells. So there are a couple of drugs being tested also in humans at the moment to see if that's a potential to make somebody younger. We are also looking at novel compounds to improve cognition as one of the outcome parameters, but also others. And we are very interested in certain pathways. For example, the GSK3 pathway, the glycogen synthesis kinase 3 inhibitor pathway. Here you see the mechanism, how it works. So you also see insulin again being included in there because it's an insulin regulating pathway. And what we were interested in, where do we find these kind of material which we could, for example, add to our diet to influence that pathway, which are associated with improved cognition. And we found a couple. You can find them in nature. For example, curcumin or sea cucumber or acetic acid. So there are lots in potential drugs or next drugs or small molecules we can use to change hopefully cognitive outcome parameters in human beings, and there was also the aging trajectory. We are doing and investing at the moment also in alpha-ketoglutarate. Here you see the mechanism of alpha-ketoglutarate, so it can be supplemented in pills with the regular diet, for example. Alpha-ketoglutarate is very likely to reduce oxidative stress, and there was interfering with the aging process, but is also involved, for example, in muscle repair and growth and stem cell regeneration. And our hypothesis is, because this is the RCT being ongoing, that AKG is influencing very positively lots of organ systems, and there was also aging in the human body. So hopefully I gave you a little bit an overview about how to identify and how to intervene, and gave you a little bit an insight of what the future in healthcare might look like. This is a summary, so hopefully we will all work on Geroscience 2.0, which really means that I, as an internal medicine specialist, will not per se see patients with diabetes, but I can prevent diabetes, and I can really interfere in the aging process, which is then summarized in longevity medicine. We are setting up at the moment the Longevity Medicine Society. If you want to join and you're interested in the field, please let me know. Thank you for your attention.
Thank you very much, Professor Maier. If we have some questions for Professor Maier, please.
Seems to be clear.
I think I have a question, Professor Maier. Because you spoke about lifestyle as a hallmark of aging, what is your opinion about caloric restriction, please?
Calorie restriction is a very important one. So there are two different things. There's calorie restriction, which means, in terms of definition, there are different definitions, but that you eat 50% less from what you would like to eat, but making sure that you get the micronutrients, etc. And there's lots of evidence that even in primates, but also in mice and rats, calorie restriction works to increase health span by around about 20 to 30%. So it works. It's, I would say, to implement it in our daily life, very difficult. Not many people will eat 50% of what they would like to eat. And there the idea from intermittent fasting came in, and intermittent fasting has the idea that you eat much less or nothing and just drinking water for a couple of either hours or days, so it's really fasting, and then eat normally as you would like to do in another period of time. And the idea about intermittent fasting is that you give the body a little bit of a period of rest to prepare, to prevent and to repair all the damage which occurred, while not being always stimulated by eating, and then you have the period of eating again, where you can really stimulate your body on protein synthesis, for example, for your muscle, because you need proteins, you need your food to regenerate your muscle, but having a period of time for repair, and not being involved in your eating habits. So I think it's quite interesting. I must say that I do the intermittent fasting, or did it already for 10 years without knowing, because I have never time to eat breakfast. So, and one of the schemes of intermittent fasting is, for example, to really skip the breakfast and have your first meal at the at 2 o'clock, for example, a little bit later than lunchtime, and then another meal before in the evening. So maybe it helps. I'm not sure. It's NS1. I'm feeling fine, but there's lots of evidence that the intermittent fasting now also works. For example, in heart failure patients, there's huge amount of studies now ongoing in America, and I think that's really a way which could be implemented for a broader audience. And I think caloric restriction might be difficult, at least for me.
Thank you very much for your answer. If we have some more questions for Professor Maier, please.
Great presentation, Professor Maier. Thank you. All you presented was excellent, and we will try to put in and apply what you presented in this study. Thank you. I have no further question.
Yeah, thanks for your comment. But most importantly, maybe then a remark, if you're interested in the field, we need much more, I would say also clinical implementation. If you are interested, let me know if you want to be part of one or the other initiative.
Thank you. Some other questions, please?
Anything?
Is an estimated time for the senolytics to be approved?
Look, first they need to work, and then they are going to be approved. And of course, that will be a long time lag, because you need all the regulatory systems like the FDA or the EMA to approve drugs. So first, we really have to make sure that there is that there's evidence that it works. So either decreasing the biological age or decreasing the incidence of certain diseases or even cure diseases. The senolytics are being tested also in diseased populations, for example, with osteoarthritis, arthrosis, or lung diseases. And once we have these data, so internationally, then there's the next step, of course, to then approve it and to roll it out. The trajectory of senolytics a little bit slower than the one of a COVID vaccination, for example, which was amazingly fast.
There are also available on the market some other supplements that claim that they can influence the aging process, because the supplements had another kind of legislation to be approved, but generally they use plants, and they're plant-based generally.
Yes, that's true. There's lots already on the market. So as I said, it's really a booming business. There are lots of supplements on the market. Look, if you would ask me, do you take it, or would you advise to take it? I would be very cautious in doing so, because as I showed you, there is a little bit of evidence in humans, but not the vast amount of evidence. And what's very important that we need to really sort out in the next coming 1 to 5 years is, what should you really take at what point in time? So it might be that a 40-year-old might need something else than a 70-year-old or an 80-year-old. And what is the dosage of it, and what is the timing of it? As we would normally do while looking for medications for diseases like cardiovascular disease or hypertension or diabetes, we also need to do that in the longevity field to really target aging as a disease, and there was also have appropriate measurements and designs to test what's working and what's not working. But the first steps are made, I would say. We know why we are aging, and of course this is the first, it's in young field, so we have lots of evidence, or gained evidence in the last 10 to 20 years how the hallmarks of aging really look like, but that doesn't mean that there are other hallmarks and we will learn even more, but at least we learned enough to now go into the intervention fields in humans, because there is a huge amount of evidence in animal studies that certain supplements, certain medications work to increase the health span and the lifespan as a side effect. And now we have to translate that into human beings. And that's what we are doing at the Center for Health and Longevity at the National University in Singapore. And of course, also with lots of international collaborators. And hopefully this will be the basis for longevity medicine. Once again, we are starting that society to really bring healthcare professionals together to increase knowledge, to write guidelines, and to move the world, not the world, but the field further.
Thank you very much for your response, your answer. If we had some other questions for Professor Maier. So as I see, there are no other questions for Professor Maier. We thank you again for your presentation and for your kindly response for our event. Thank you, Professor Maier. And if you can join the other link that we sent by mail. Thank you very much. Thank you very much again. And thank you very much for you all. Also, thank you.
Okay, stay healthy and take a step.
Okay.
Every step is good. Bye-bye.
Bye-bye.